Hello everyone, I'm Masashi Kumagai from Tokyo University. The paper title is Combinatorial Clustering based on an externally defined one-hot constraint. First, I will talk about the background of the research. Annealing algorithm can solve a combinatorial optimization problem quickly. The combinatorial optimization problem is a problem to find the optimal solution from combinations of multiple variables. Symmetric annealing, called SA, probabilistically searches for the optimal solution. Moreover, quantum annealing, called QA, searches for the optimal solution using the quantum effect. The demand for high-performance clustering in data science is growing, as it is widely used in the analysis of big data. Clustering is often considered a combinatorial optimization problem. I will explain combinatorial clustering using the annealing algorithm. In the annealing algorithms, the combinatorial optimization problem is represented by a quadratic unconstrained binary optimization QO problem, which minimizes an objective function of a quadratic polynomial described by binary variables. In combinatorial clustering, the objective function and the constraint function are formulated to the QO function by the method of the Lagrange multiplier. This figure shows combinatorial clustering using symmetric annealing on a CPU when the number of data points is 20. Combinatorial clustering succeeds in classifying the data points. However, the QO formulation by using the method of the Lagrange multiplier is problematic. When the problem size is large, the same QO function as before is given. The lambda in the constraint function must be set to a large value, but current quantum annealers can only handle low bit precision. Therefore, the objective and constraint functions are compressed in the QO function, and the objective function loses its properties. As a result, the constraint is satisfied, but the objective function cannot be optimized. This figure shows the results of clustering when the number of data is 200. Clustering fails if the problem size is large. This research aims to improve the quality of clustering. To achieve this objective, we propose combinatorial clustering using a QO solver that can externally define the one-hot constraint independent from the objective function. A one-hot constraint is a constraint used for combinatorial clustering. The proposed method minimizes the QO function that contains only the objective function and controls the one-hot constraint outside of QO. In this way, the proposed method focuses on the search for solutions satisfying one-hot constraints. I gave the background of the research. After that, I talked about the objectives of the research and the approach to achieve them. Next, I will explain the two proposed methods and show the results of our experiments. Finally, I would like to talk about conclusions and future work. First, I explain how to minimize a QO function containing only the objective function by SA. This figure shows an image of the SA algorithm. Hamiltonian of the y-axis is the value of the QO function. SA search for smaller Hamiltonian of combinations by gradually varying the elements that make up the combinations. However, if only smaller solutions is adopted as more optimal solution, the solutions will fall into a local optimal. Therefore, SA adopts a probabilistically larger solution to escape from the local optimal solution. This allows us to find the right optimal solution. However, the optimal solution may not satisfy the constraint in this way. For example, when clustering is performed without satisfying the constraint, a data may be allocated across two clusters. We solve this problem by using the external constraint. The optimal solution is in the range of the one-hot constraint. Conventional SA is executed until a solution that satisfies the one-hot constraint is found. After that, SA searches for a solution that always satisfies external constraints. All the data are properly assigned to each cluster. Next, let me explain the one-hot constraint. In combinatorial clustering, the variable QA is 1, data point I belongs to cluster A. When the data are classified as shown on the left, the value of the variables QA are shown on the right. The one-hot constraint is satisfied if there is only one value of 1 in each column. The proposed method uses a Cubo solver that can externally define the one-hot constraint independent from the objective function. In the Cubo solver, a constraint is satisfied by the bit flip operations of SA. Hereafter, the algorithm of simulated annealing with an external constraint is called SAEC. In this algorithm, firstly, a variable QAI to flip is selected. In this table, only one variable among Q1i, Q2i, and Q3i is 1, and the others are 0. When the number of 1 in Q1i to Qki related with QAi is 1, if a variable Q11 equal 1 is flipped. All variables Q11, Q21, and Q31 become 0, which violates a constraint. Data point I equal 1 does not belong to any cluster. When QAi is 1, to prevent the constraint violation, SAEC controls the solution to satisfy the constraint by simultaneously flipping either Q2i or Q3i when Q1i is flipped. This allows SAEC to search for solutions by satisfying the constraint efficiently. Combinatorial clustering using annealing algorithms needs to generate a Cubo matrix that represents a Cubo problem to be optimized by SAEC. As it is difficult to generate the Cubo matrix, PyCubo has been developed to save the effort of generation the Cubo matrix by programmers. However, the execution time of PyCubo is long because the system computes the Cubo coefficients automatically. We propose a method to generate the Cubo matrix using a method to assign Cubo coefficients to the Cubo matrix effectively. This method is called compact Cubo definition (CQD). CQD accelerates the generation of the Cubo matrix because of the elimination of the calculation of the Cubo coefficients. Also, the proposed method uses CQD by lambda equals 0 to exclude any effect of the constraint function. To execute the proposed method, an SX or Tsubasa system is used. The system consists of a CPU, Intel Xeon, and a VPU NEC vector engine. The solver that executes SAEC in this system is called Aura Simulated Annealing, ASA. This paper compares the proposed method with 4 methods. One method is the method using QA on a QPU quantum processing unit. However, QA cannot be performed if the problem size is large because the number of qubits is limited. Therefore, a hybrid solver that combines QA on a CPU, a QPU, and conventional computation on a CPU is used for larger problems instead of using only QA. This paper uses DF's Leap hybrid sampler, Leap, as a hybrid solver. Leap is used to be as a DWeb Ocean SDK Python interface. The other methods are k-means, k-means++, and spectral clustering on CPU by scikit-learn. The dataset used to evaluate all these 5 methods is an artificial dataset generated by make probes in scikit-learn and toy datasets. The toy datasets are closer to real datasets than artificial ones. In Iris, there are 3 classes of 150 instances, 50 each, and the number of attributes is 4. In Wine, there are 3 classes of 178 instances. Each of the 3 classes has 59, 71, and 48 instances. And the number of attributes is 13. The quality of a clustering result is evaluated with the execution time and cost as a value of an exact objective function. We visualize the clustering result of combinatorial clustering. The number of data points is 100 and the number of clusters is 6. The conventional methods fails. This is because the constraint function in the cube matrix causes a problem of bit pressure. While the proposed method succeeds in clustering the data points because of avoiding the problem of bit pressure by the external constraint. Next, we evaluate the quality of clustering results. This table shows the qualities of the results of the conventional method, the proposed method, k-means, k-means++, and spectral clustering on CPU. The smaller cost is, the better the clustering result is. The proposed method is better than conventional method. This is because the conventional method includes a constant function in the cube matrix, making it difficult to successfully perform combinatorial clustering due to the limitation of pressure on the hardware. Also, the proposed method is better than k-means, k-means++ spectral clustering. This is because the approximated objective function in k-means is trapped in the cache optimal solution. Next, we evaluate the execution time of combinatorial clustering. This figure shows the execution time of the proposed method and the conventional method. Each method is executed on both the CPU and the VPU using ASL. The number of data points is varied from 100 to 1500, and the number of clusters is 6. The proposed method takes a longer time than the conventional method. This is because the proposed method needs to satisfy the one-hot constraint by the bit flip operation algorithm. In addition, both the proposed method and the conventional method running on VPU is faster than on CPU, because the VPU uses vector operations to process large problems faster. These figures show the execution times of the proposed method, the conventional method, and clustering methods in scikit-learn when the number of data points are 10 and 1000. The number of clusters is 6. The conventional methods on a QPU is lower than those on a CPU and VPU. This is because bit pressure over quantum annealers is not sufficient. In addition, the conventional method on a CPU reduces the quality as much as QPU when the problem size is large. The proposed method of scikit-learn is faster than combinatorial clustering. This is because a cache optimization algorithm is used to reduce the computational complexity. In the same way, large datasets that cannot be executed on a QPU is evaluated on a CPU and VPU. The proposed method can find the optimal solution the methods of scikit-learn. As the problem size increases, the quality of the proposed method remains high. This figure shows the speed-up ratios of the cube generation. The number of data is varied from 10 to 100, and the number of clusters is 2. The x-axis indicates the number of data points, and the y-axis indicates the speed-up ratios of the proposed CQD implementation to the conventional PyCube implementation. The speed-up ratio becomes huge as the problem size increases. This is because the execution time is reduced by giving the cube coefficients directly to the cube matrix. The speed-up ratio is up to 10,000 times faster. I would like to conclude the presentation. Combinatorial clustering using annealing algorithms has been drawing attention. However, combinatorial clustering fails because of the limitation of the bit precision. This research proposes combinatorial clustering using the cube solver with the externally defined constraint function and the technique of the cube generation by deriving the regularity of cube coefficients. The evaluation results show that the proposed method can improve the quality of clustering results compared with conventional clustering methods such as k-means. In addition, the proposed method shows 10,000 times faster execution of the cube generation than the conventional technique. As future work, we would like to apply the proposed method to other problems or applications. We would also investigate the use of the one-hot constraint or quantum annealer. Thank you for listening. If you have any questions, please contact me.